1996 E&M number 2. This is a case where they've given us a capacitor, 2 switches, 100 ohm resistor, and another capacitor that's 3 times bigger. And they're telling us the capacitor 1 is initially charged to 50 volts. So this guy is at 50 volts. Capacitor 2 is initially uncharged. Alright, so the final charge is on the positive plate of each capacitor after we've reached equilibrium. Okay, so when we reach equilibrium, the voltages are going to be equal to each other. So that'll be Q1 over C1 equals Q2 over C2. And we have to conserve the charge. So Q1 plus Q2 equals Q total. Well, what's Q total to begin with? Well, Q total is here measured from the 50 volts and the 4 microfarads. So Q total VC, that's 50 volts, that's 4 microfarads, so that's going to be 200 microcoulombs. Coming back over here, Q1 is going to be C2 over C1 equals Q2, and C2 is 12 micro, C1 is 4 micro. The 2 micros are going to cancel out. 12 over 4 is 3, so 3Q1 equals Q2. We can take that relationship and plug it into here. So Q1 plus 3Q1 equals 200 microcoulombs. 4Q1 is 200 microcoulombs. That means Q1 is going to be 50 microcoulombs, which, taking that guy back over to our original equation, we're going to have Q2 is 3 times that, also known as 150 microcoulombs. All right, part B. Determine the difference between the initial and final stored energy. Well, we've got our 2 charges here, and the original potential energy is going to be 1/2 CV squared. They gave us C, they gave us V, so that'll be 1/2 4 micro 50, don't forget to square that, and that will get us 5,000 microjoules. So 1/2 4 is 2, 2 times 50 squared gets us 5,000. All right, the final is going to be, well, we don't know what the final voltage is, but we do know Q squared over 2C. And we now have that charge split between our 2 capacitors. So we have Q1 and Q2. So this will be 50 micro squared over 2 times 4 micro plus 150, it's a 150 micro squared over 2 times 12 micro. Multiplying those guys, adding them up, gets us 12, that's a 5, 1250 micro. Wow, handwriting just not going well today. That is 1250 microjoules. And that's not what they asked for. What they asked for was the change in energy. So the change in energy, yep, the difference between the initial and the final is negative 3750 microjoules. Now, you can multiply this by times 10 to the minus 6th. You can move it over and do 3.75 millijoules, just so long as whatever you get works out to be the same after you account for all of the differences in the powers of 10. All right, part C. An equation that relates the charge on capacitor C0, its time derivative, which is the instantaneous current. How nice of them to tell us that. And then various parameters. Well, this is a really annoying way of saying, write down a Kirchhoff's loop rule equation for these guys. So we're going to have V from capacitor 1 minus, you know what, let's start with just the voltages, minus the voltage drop across the resistor minus the voltage drop through capacitor 2 equals 0. All right, now V1 is going to be Q1 over C1. The voltage drop across a resistor is current times the resistance. The voltage drop across V2 is going to be Q2 over C2 equals 0. Now, Q2 is not allowed to be in there. Why not? It's not one of the givens. Q1, the charge on capacitor Q1. Q2 is not the charge on capacitor Q1. So we're going to have to go back to part A and look at the relationship between the total Q, which is Q1, and the charge on Q2. All right, so this guy is going to have to be Q total minus Q1 over C2. And what is Q total? Again, go back to part A. Q total is the original voltage across capacitor 1 times capacitor 1. So we're going to have to get rid of Q total again and write in the original voltage. I can't believe I started to say velocity. The original voltage times capacitor 1 for that guy. And then we have this guy. And then we have Q1 over C1. Now, that's really annoying, and we're not even done yet. Why? Because they say the time derivative. I is not the time derivative. So we're going to have to get rid of I, and we're going to have to replace it with dq dt. That is the time derivative. And now we have finally satisfied the conditions for part C, where we have rearranged things. And again, keep in mind, we just started with the Kirchhoff loop rule, and we said capacitor 1 is essentially our battery, resistor brings it down a little bit, capacitor 2 brings it down a little bit more, and now we're back at the ground. I'm going to have to pause and clear things out so that I can have enough space to do parts D and E. All right, part D. Energy dissipation. The rate of energy dissipation is also known as power. So power, why am I not red here? So power is I squared R, and they gave us I. So that will be I naught squared R e to the minus 2t over tau. And they'll probably want 0.5 for this, and 3 times 10 to the minus 4 seconds for tau. Part E, how much energy is dissipated? Well, in order to figure that out, you can do one of two things. Number one, you could go back to part B. The total amount of energy dissipated is minus 3750 microjoules. Or you could say the energy dissipated is the integral of power as a function of time, and then you can take this expression here and integrate it between 0 and a very long time later. So that will be I naught squared R integral e negative 2t over tau dt from 0 to a long time later. Keep in mind, a long time later for an electron could be a couple of microseconds. So we're going to have I naught squared R e to the minus 2t over tau evaluated from 0 to a long time later, and then divided by negative 2 over tau. which, when you do all of this, gets you the positive version of 3750 microjoules, because part B is how much energy did we lose from beginning to end, and part E is how much energy got turned into heat. It's the same question, just missing a minus sign.